class we're going to start looking at compression. Compression is a reversible conversion of data to a format that requires fewer bits. Now the purpose of compression is to make it easier to store or to transmit information. So if it takes up less space, it can get from A to B quicker. Or if it takes up less space, we can fit more of it on a CD or on a hard disk or whatever, or on a website for that matter. Either way, there's some cost associated with storing information, whether it's transmitting it or storing it. There's a cost there, and what we want to do is to reduce that cost. Imagine for a minute that the post office didn't charge for letters by weight. Suppose that the price was determined exclusively by the size of the envelope. So imagine if you had an A4 letter and you put that into an A4 envelope, you might pay a lot. But if you folded up that letter so that it fitted in a smaller envelope, then you would pay less. So you could transport the letter from A to B for less if you folded it up. And that's a bit like compression. Compression is a bit like folding up the information in itself so that it takes up less space. Now, just like a folded up letter is difficult to read, similarly, data that's in compressed form isn't very accessible. But what you can do is you can use a decompression algorithm to get the data back again. And decompression is like unfolding the letter, so you get back the letter that you started with. And so decompression takes the folded up data and expands it out again so that it can be used. Now the first kind of compression we're going to look at is text compression. And text compression is very clever. But what I'd like you to do now, if you have time, is to stop this class and go away and find someone who's willing to play a game of hangman with you. And as you try to guess the movie or the song or whatever it is, make a note of the letters used to guess and the order that they're used. If you can, go away, do that and come back. So let's imagine this is a game of hangman here. The first guess here is A. A is always a good guess, but unfortunately there's no A here, so we're starting to build the gallows there. Next up we have E. E is always a very good guess as well. And we have an E there, so... Okay, if the player guesses O, it turns up in a couple of places there, so getting closer. And T, again, always a good guess. This gives us the start of it here. So that certainly looks like a the anyway. I is also in this title here. N is in there. There's no R, which is a bit of a surprise. R is often a good guess. There's an S. At this point it might be possible to guess what it is, especially since the first word is very likely the. Sure enough, it's a the. There's a H in there. Okay, it should be real easy now. If you can't get it now, you're really bad at this game. So if you guessed the sound of music, that was right, and our little man is happy out there because he's free. What's interesting here is not so much the actual title, but the letters that were used to guess and the order that they were chosen in. When you play this game with someone, their first guess is never Q or X or Z. It's typically an E or a T or a H, O. Those are all good guesses to start with. And the reason they don't lead with X or Z is because those letters are fairly uncommon in English. E and T are very common, for example. And it turns out that in English, some letters occur much more frequently than others. And that's a fact that we can exploit to try and achieve some compression. So which letters occur more commonly than others? One of the first people to twig this was Samuel Morse when he was devising Morse code. He realized that some letters occurred much more frequently than others. And that was a feature he wanted to use in the code that he was trying to devise. He came upon a very clever way of approximating the frequencies of the letters in English. He took himself off to a printer's and had a look in the tray of type that printers use for setting text. And he noticed that the typical printer's tray of metal type had many more letter E's than any other letter. And so he counted them up, and he used that as an approximation for the frequencies of the letters in English. He figured that printers knew their business and they weren't going to leave themselves short when it came to having all the letters that they needed. So he came up with this table here and used this when devising Morse code. That's why in Morse code, E and T have the shortest sequences. If you're interested, you could go away and find the sequences of dots and dashes used in Morse code and see if the lengths of the sequences bear some relationship to the table here. Other evidence that some characters occur more frequently in English than others can be found in the game of Scrabble, of course. In Scrabble, you get different points for making words with different letters. If you can make a word with a Q, or an X, or a Z, you get more points than you do for using the letter E in a word. So you could do your analysis in a couple of different ways, but in any event you're going to come to the conclusion that some letters occur more frequently than others. And certainly E and T are way up there at the top. So how does knowing that some letters occur more frequently than others help us? Well, if we have an ASCII style code where we have, say, 8 bits for each character, then all of the characters have bit sequences that are the same length. So E has 8 bits, T has 8 bits, Q and Z and X, they have 8 bits as well. It's possible to devise an alternative table where the sequences of bits for the characters are not all the same length. And so what this table does is that it assigns the shortest codes to the most frequently occurring characters and the longest codes to the least frequent characters. That's a bit like robbing Peter to pay Paul though, because if you make some sequences much shorter than usual, you're going to have to make others much longer than usual. But it turns out that because the frequent characters have the shortest codes, the savings that you make there are multiplied over and over and over again. Whereas the cost associated with giving some characters extra long sequences is incurred fairly infrequently. Now, the concept behind variable length codes was known for quite some time. But Huffman was the person who figured out the algorithm for producing optimal codes. So let's take a look at this simple language here that has only 8 characters in it. Since there are only 8 characters, we'd need to use only 3 bits to give each character here its own bit sequence. Now, in this language of 8 characters, some characters occur much more frequently than others. We can see here that there are 60 E's for every 1 Z, and there are 60 E's for every 10 T's. So there are 6 times as many E as there are T and A. And of course Z and D and Q are fairly infrequent. P, B, A and T are in the middle there. And then E occurs significantly much more frequently than others. Now this example is fairly contrived, but it will illustrate very well how Huffman coding works. Now what Huffman coding tries to do is it tries to build up a tree, and the leaves of the tree will be the characters in the language. Now it does this by combining parts of the tree to make larger subtrees and then eventually building one large tree. We start by lining up all of the characters in order of their frequency, with the least frequent at the front. We take the first 2 symbols and we form a subtree. and we give that subtree a value equal to the sum of the frequencies of the two parts. So this subtree here now has a value of 3. We line up all the subtrees again in numerical order, although it turns out that these are still in the correct order. We then combine the two smallest subtrees into a larger subtree, and that subtree has a value equal to the sum of the two parts that made it up. So here this subtree now has a value of 6. We line them all up again in numerical order, but as it turns out these happen to be in order anyway. And again we combine the two subtrees with the smallest values together to make a larger subtree, and its value will be the sum of the two parts. So this subtree here now has a value of 12. Our next task now is to line these up in increasing order. So now we have 8, 10, 10, 12 and 60. So we combine the two subtrees with the smallest values, and the value of the new larger subtree will be the sum of their parts. So this subtree has a value of 18. Again, we line them up in increasing order, and so now we have 10, 12, 18 and 60. So the two smallest subtrees here now are the ones with the values of 10 and 12. So we'll combine those together into a larger tree, and that tree has a value of 22. We line these up in increasing order, and we'll have 18, 22 and 60. And we combine the two smallest subtrees. The new subtree has a value of 40. Now there are only two subtrees left, and so we join them together to complete the tree. Now looking at this tree, you can see that the infrequently occurring characters are way down at the bottom. They're very far from the top of the tree, where the distance from the top to the most frequently occurring characters, like E, is very short. And so we use this feature of the tree to build up the code. So how do we get the bit sequence for each character? Well, starting at the top of the tree, we follow the path to the character. If when going from one node to the next, we take the left branch, well then we assign that a 0. If we take a right branch, we assign that a 1. And so in this way, we can assign a bit sequence to each character. To get to the letter B, for example, we have to go left, 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 which is 0, 0, 0. To get to A, we have to go left, left, right, which would give us 0, 0, 1. We get to T from the start by going left, right, left, which gives us 0, 1, 0. And we get to Z by going left, right, right, left, 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 which gives us 0, 1, 1, 0, 0, 0. Now you notice that the code for Z is quite long because it's very far down the tree. D is left, right, right, left, left, right, which is 0, 1, 1, 0, 0, 1. Q is 0, 1, 1, 0, 1. P is 0, 1, 1, 1 because it's left, right, right, right. Now E is just 1. And you notice that E is the most frequently occurring character, and it has the shortest code. Z is the most infrequently occurring, and you can see that it has one of the longest codes. So irrespective of the frequencies of your characters, applying the Huffman coding algorithm will give you a tree that gives you the optimal codes. So now we can use these variable length codes instead of the fixed length codes. So instead of using 3 bits for E, we just use 1 bit. So every time we have an E, we save 2 bits. But of course, by using the variable length code that has 6 bits for Z, it's costing us an extra 3 bits every time we use a Z. But of course, we've 60E for every 1 Z. So we save 2 bits 60 times and we lose 3 bits once. And so that's how variable length codes can save bits overall. So Huffman coding is one of the most useful compression schemes. It's used a lot for text and can typically reduce a text document to maybe 1/3 of its original size. Now you can see that the algorithm for building up the tree and devising the variable length code is quite complex. So we don't use Huffman coding for compressing web pages because that would take too long. But Huffman coding does crop up all over the place in other compression algorithms for images and video and stuff, and we'll see some of that later. So the main point with variable length codes is that the most frequently occurring characters get the shortest codes, and the infrequently occurring characters get long codes. And that gives you a saving overall.